This windmill is located in the Rheinische Open Air Museum in Kommern. When it received a new crossblade, the millwright's work was captured on film. The four blades are attached to two massive oak beams. On the mill roof, the cap and wings are inserted crosswise into the head of the mill axle. A massive beam structure at the rear of the mill allows the cap and wings to be turned into the wind. The wind power is transferred via the axle into the interior of the mill. This is the same windmill before the crossblade is attached. The axle head on the roof of the mill is ready to receive the two wings. The wings must be pulled into these two openings in the axle head. The first wings lies on the ground, to which the millwright and his assistants attach the end of a pulley. A pulley and a hand-operated earth winch take on the function of a modern crane. With these simple tools, the wings will be hoisted up to the mill roof. Now the men assemble the earth winch. The earth winch consists of a wooden frame and a matching axle. During preparation, a rope is attached which allows the beam to be pulled up straight. Two strong wooden poles transfer the muscle power to the earth winch. The men begin by hoisting the first beam. A pulley guides the hauling rope in the desired direction. As the assistants constantly turn the earth winch, the beam slowly lifts off the ground. The load hangs from the lower pulley on the block. The men gradually pull in the hauling rope using the earth winch. The rope, which was attached during preparation, holds the beam in the correct position. Finally, the tip of the beam reaches the shaft head. Here the millwright guides it into the opening in the shaft head. When the tip of the chest piece protrudes slightly beyond the opening, the millwright must temporarily secure the beam. He uses an iron rod, which he inserts through a hole in the chest piece tip. This is necessary because the pulley block has shortened so much that it needs to be stretched out again. To do this, the assistant detaches the pulley block from the center of the beam and reattaches it to its lower end. The chest piece is pushed into the shaft head. The millwright's assistant connects the chain to the pulley of the cable pulley. The men can now operate the earth winch again, until the chest piece protrudes a little further from the shaft head hole. Then the millwright hammers in the eye bolt, which will later be used to attach the wings. The chest piece beam slowly slides through the box-like guide in the shaft head. Finally, the chest piece has reached its final position. Now the millwright must wedge it firmly in place. The millwright hammers the wooden wedges into only two sides. On the other two sides, the piece must fit snugly against the opening in the shaft head, as can be seen here from the hood window on the left. In order to drive the wedges into the side of the shaft head that is now facing downwards, the millwright has the breast piece rotated 90 degrees. The oak beam is therefore fastened with wedges on both sides in the same place. The second breast piece is lying on the ground, ready with the wings attached to it for testing. Each wing consists of a narrow fore stern with continuous board cladding and a wide rear stern, which looks like a ladder with its rung-like wooden slats. The connecting piece between the fore stern and rear stern is used to mount them on the mill. The pair of wings must be taken apart. First, the men remove the windboards from the fore stern. Iron bands hold the breast piece and wings together. Here the narrow fore end and the wide rear end of each wing can be seen. As soon as the men have loosened the straps, they can carefully lift the wings off. The breast piece is made of oak, a particularly strong and durable type of wood. It is 14 meters long in total. Using a chisel, the assistants remove the oarlock from the breast piece beam. They then attach the lower pulley of the block and tackle to it. Using the earth winch, the men pull in the pulley rope of the block and tackle, which is attached to the lifting load with the loose pulley and to the mill shaft with the rigid pulley. The breast piece slowly lifts off the ground. By turning the earth winch, the entire cable pulley is shortened and the load is lifted. Another millwright directs the work from the ground. After further turning, the beam extends beyond the shaft head and is secured again with the iron rod to prevent it from slipping back. The block and tackle has become too short. The assistant reattaches it to the lower end of the beam. After further lifting, the millwright drives in the thorn pin. Then from the ground, the beam is moved into the correct position. The front piece is again wedged on two sides of the axle head. Then, from the ground, the mill's brake is released to rotate the beam into a horizontal position. This mill comes from Lower Saxony and is a so-called octagonal mill. It is considered the forerunner of the stone tower windmill, which was built in the Rhineland, particularly in the 19th century. Once the front piece is in the correct position, the millwright can drive in additional wooden wedges. To build a mill, the millwright had to master a wide variety of craft techniques. For this reason, millwright apprentices learned wheelwrighting, turning, and carpentry skills over a 5-year apprenticeship. Once the two front pieces are firmly wedged into the shaft head, the two pairs of wings can be attached to the front pieces, one after the other. Each wing is not made in a single plane, but is slightly curved. The measurement, after which the deflection in the blade was calculated, was the secret of every millwright. The blades are also raised with the help of the earth winch and the pulley. Only 2 men are needed at the earth winch. The blades must be strong but light. The millwright usually used pine or spruce wood. Pitch beam and larch could also be used. The wing cross on the shaft head captures the wind. The mill shaft or axle then transmits the power to a system of gears inside the mill. In this way, one or more grinding gears inside the mill receive their driving power. The blade has reached its seat on the breastpiece. Now the millwright's assistant can connect the breastpiece and the blade together. On the ground, helpers prevent the blade from slipping. The 3 men ensure that the upper end of the blade lies exactly against the shaft head. Once it is correctly seated, the rest of the blade must be brought into place. Then the millwright's assistant connects the blades and the breastpiece with iron bands. You can clearly see how the blade rests on the breastpiece. Each blade is firmly attached to the breastpiece with 2 bands. The iron bands are lying on the ground ready for assembly. The oar locks and iron bands provide a stable connection between the breastpiece and the blade. The first blade is attached to the breastpiece. The mill shaft is turned further to accommodate the second blade. The ground winch is also used for this. The blades are attached in reverse order. The men carry the counterpart to the first blade to the mill hill. This mill originally stood in Cantrip, a town near Osnabrück. It is one of the few buildings in the Rhenish Open-Air Museum that does not originate from the Rhineland. All Rhenish windmills are preserved buildings and may not be demolished. After the Second World War, the Cantrip mill was hardly used because wind power was no longer profitable. It was disemboweled in 1969 and rebuilt 2 years later in the Rhenish Open-Air Museum. Meanwhile, the second wing has also been raised. It must now be firmly locked into the tacks. The breastpiece and wings are connected with iron bands. The pair of wings, now mounted in the outer axle head hole, are called field rods. With the help of the earth winch, the mill shaft is turned further to attach the wings to the inner axle head hole. These are called house rods. Before attaching the house rods, the men take a break. Then the next wing must be raised. The trade of the millwrights, also called mill doctors, was a traveling business. The millwrights often did not return home for several weeks, as their customers lived far apart and in remote areas. Larger jobs, such as building a roof or a wing cross, were not carried out in their home workshop, but directly on site at the mill. All but one of the wings are fully assembled. The narrow fore and aft and wide aft end of each wing can be clearly seen. Overall, a wing is approximately 12 meters long and 2 meters wide. The crossblade is one of the most sensitive parts of the windmill. This is where the most frequent and most expensive repairs occur. Storms and thunderstorms in particular can shorten the lifespan of a blade. Therefore, the windmill operators always monitor the weather very closely in order to turn the wing away from the wind. The last blade is raised. As can be seen in the foreground, the tip of the blade is slightly slanted. Without a top, the blade does not utilize the wind power sufficiently. Wind chutes, as they are called in mill jargon, make the wind rush. The men need a total of 2 days to fully assemble the crossblade. Good wooden blades have a lifespan of 10 to 15 years. The Kingtrepper windmill has a modern cast iron shaft head instead of a wooden one. The number 1903 on the axle head indicates the year of its construction. The mill itself, however, is older. Wooden slats are ready on the ground to make the blades finally ready for use. This mill has so-called lathe blades. In contrast to the sail wings, which the miller covers with canvas for milling, the lathe wings consist of movable wooden flaps. The men have to screw the flaps tight on both sides at the rear stern. The individual flaps are made of wood and are mounted on a pull rod, a long wooden slat. Because each individual flap is connected to the pull rod, the luves can be opened and closed. Another luve flap is handed up to the millwright and his assistant. First, the men fit it in the rear stern. Then the assistant screws the hinge of the flap to the pull rod. Meanwhile, the millwright inserts the luve between the outer strut of the rear stern and an additional slat, which he then screws tight. The pull rod leads into the interior of the mill via another hinge on the shaft head. In this way, The miller can easily regulate the surface area exposed to the wind from inside the mill. This louvre system became widespread in Germany from around 1900. It is one of a series of inventions made by millwrights and engineers in the 19th and 20th centuries to better utilize the wind. Ultimately, however, wind power could not compete with the new energy sources of the industrial age. Steam engines, and later electric and diesel engines, took over from wind and water power in the 19th century. After the Second World War at the latest, most of the Rhinish windmill owners gave up their mill operations. As a result, the millwrights also lost their livelihood. The few millwrights who mastered the old techniques are restoring the surviving mills, which are now listed as historical monuments. The louvre flaps are now attached to all 4 blades. The millwright releases the mill's brake using a chain. In a final step, he checks the correct balance of the rotor blades. The blades rotate smoothly and evenly. For now, the millwright's work is finished. Please like and subscribe. Also, see other historical videos we have translated and uploaded. Thanks for watching.